So welcome to the online picture language seminar. We're very pleased today to have Shawn Cui, and I announced that the next 5 seminars are scheduled out to July 7th. We have Elizabeth Kwasson next week, then a West Coast talk from Matt Hastings, who's getting up early. Changwei Liu will talk the week after that. Robert Rosendorf, another West Coast talk, and then Marius Junge. So Shawn is at Purdue University, is well known for his work on higher category theory and topological field theory, and also on quantum error correction. And we're very pleased to have you here this morning. So I'll stop my screen share and let you take over. Shawn.
Okay, thank you very much, Arthur. Let me try to share a screen. Okay, can you see a wide screen?
No, now we do.
Oh, okay, great. Okay, so thanks everyone for attending my talk, and I hope everyone has been enjoying staying at home and listening to all kinds of Zoom talks. And also feel free to interrupt me if you have any questions. I'm not sure if I can monitor the questions from the chat right now, but I'll stop periodically to ask to see if there are any questions. And again, feel free to stop me if you have any questions. Okay, so I'm going to talk about basically, oh, let me change the color. Kitaev's model as a error correcting code. And this is a joint work with a pretty long list of authors. So there are David Ding, Xi Han, Jeff Pennington, and then Reynard, Brandon Rihon, and Shawn. Okay, so that's a pretty long list, and they are all graduate students at Stanford University. So, and also you can find the paper relevant to this talk at the following archive number. Okay, so so basically in this talk, I'm going to show that the Kitaev's quantum double model is a quantum error correcting code with macroscopic distance. And here's the outline for my talk. In the first part, I'm going to provide some overview and background and motivation, and then state exactly what I wanted to show. In the second part, I'm going to provide a review on Kitaev's quantum double model and state the main results. And in the last part, I'm going to provide a sketch of the proof of the main result. Okay, so so for now, I mean, as I said, in the second part, I'm going to provide some details about this Kitaev's quantum double model. So for now, it suffices to know that the Kitaev's model is a spin lattice model. So it is a lattice of spins with a Hamiltonian of certain types. For example, the famous toric code. Okay. And it is known that the Kitaev model realizes, or the Kitaev model is a example of a topological quantum order. Or I mean, TQO for short. Or is also called a topological phase of matter. And then as a topological quantum order, it has a gapped spectrum. Quasi-periodic excitations, or also called anyons. And you can, for example, braid anyons. And moreover, all of these properties and operations, they are stable under local perturbations. Okay, and then we can utilize these properties to perform the so-called topological quantum computation. Which has inherent fault tolerance because of the stability of this topological quantum order. Okay, so I mean, all of this is kind of folklore. All of this is kind of folklore, at least to physicists. Okay, so today, my goal the goal of my talk is mathematically justify this statement. The statement that the Kitaev model is a topological quantum order. Okay. Then of course, to make any reasonable statement, I need to first say what I mean by topological quantum order, because otherwise it's very easy to fall into a circle of arguments chasing one each other. And so I need to tell you what I mean by a topological quantum order. So some of the definitions of topological quantum order, they are kind of physical definitions, and they are not mathematically rigorous. So to make any mathematical statement, I need to provide a mathematical definition of topological quantum order. And then I'm going to show that the Kitaev model is indeed a topological quantum order. Okay, so and then now I'm going to provide you a definition of a topological quantum order, or TQO. But before doing that, let me first set up some conventions. So I'm going to restrict to the following class of lattice models. So consider a lattice of linear size L. And for simplicity, I assume that, let's just assume the lattice are either square lattice, okay? And then I'm going to assign a qubit to each edge of the lattice, okay? Or spin of dimension d. So for every edge, there is a spin living on it. Okay, and then the total Hilbert space is just defined to be the tensor product of the spins over all edges. And the Hamiltonian is equal to the negative sum of a number of terms pi, where I assume that the pi, each pi is a local projector, which means that pi only acts non-trivially on a few number of spins. For example, here I can see maybe pi, each operator pi, some term pi only acts non-trivially on the spins that is contained in this black circle. Okay, so basically pi is a geometrically local projector. So pi square equals pi. And also I assume that all the terms pi and the pj, they pairwise commute with each other. And lastly, I assume that the Hamiltonian is frustration free. Meaning that the ground state space, is simultaneously achieved as the +1 eigenstate of all the PIs. Okay, so that's the ground space. And lastly, I'm gonna define a projector P. So define P to be the product of all the projectors Pi. So this you can see that this is a projector that projects exactly onto the ground space. Okay. Okay, so here the definition of a TQO in the sense of Bravyi, Hastings, and Michalakis. So so here we assume a spin system is a topological quantum order, is a TQO, if the following two conditions are satisfied. So first of all, let me call the first condition TQO1. Okay. So so the first condition says that okay, well, maybe let me first draw a picture. So recall that we have a lattice of spins, and then I'm gonna, well, the size of the lattice is L, and I'm gonna choose a sublattice A. So here, so there is a constant alpha greater than 0, such that for any sublattice A of size less than or equal to L to the alpha, and any operator OA which only acts non-trivially within A, then we have so P OAP is equal to CP, where here C is some scalar. Okay, so that's the TQO1 condition. Basically, what this means is that so this is equivalent to say So this is equivalent to say that basically the ground space is a quantum error correcting code that corrects arbitrary errors within A. Okay, so that's what TQO1. And then here's TQO2. So recall that the projector P that projects onto the ground space is the product of all the PIs. And now let me choose a slightly larger sublattice B. So it is slightly larger than A. And let me define P sub B to be the product of all the PIs for which the support of a PI is contained in B. So this means that we only collect those PIs which act non-trivially only within B. So its support is contained in B. Okay. So here PB is apparently is also a projector. And now we consider, for the projector P, we consider its reduced density matrix on A. So namely, we trace out the complement of A. We get, so the resulting operator now acts only on A. And we can also consider the reduced density matrix of P sub B. So we require that these two operators have the same kernel. Okay, so that's the two definitions. That's the two definitions of TQO. And so with this definition, Bravyi-Hastings and Michalakis, they show that. So if a Hamiltonian H0 is a TQO, then its spectrum gap is stable under local perturbations. Okay, so roughly, so for example, if let's consider a perturbation of the form like this, where V is some local perturbation, and so I'm not going to state this very rigorously, but let's say the strength of the perturbation is bounded by J, then the spectrum of H looks like something as follows. So assume this is the initial energy, and then as we turn on the local perturbations, then the spectrum will look like as follows. Okay, so basically what this means that as long as the strength of the perturbation is small enough, then the energy spectrum will not cross with each other, and we will have a stable energy gap. And moreover, what's important is that the smallness of local perturbations doesn't depend on the size of the lattice. Okay. Okay. So basically, with this definition, and the goal of my talk is to show that the Kitaev model is a TQO. Okay. So are there any questions so far? Okay. So if there's no question, I'm going to continue. So now let me tell you what exactly is the Kitaev model. So to define this Kitaev model, first of all, I'm going to fix a finite group G. So it has elements G1, G2, and so on. And I'm going to fix a surface, sigma. This is a closed surface. So a surface without boundary. And for instance, you can think of a torus. And then I'm going to choose a lattice on sigma. Something like this. And again, for simplicity, let me assume the lattice is a square lattice, but in general, it doesn't have to be. And for this lattice, let me denote VEF to be the set of vertices, edges, and faces of the lattice. And also, as
so Shawn, excuse me, Shawn, you're always in a two-dimensional surface.
That's right. That's right. So here I'm only restricting myself to two-dimensional surfaces. Okay. Yeah, the technical requirement, I'm going to arrange the edges arbitrarily. So let's place an arrow on each edge arbitrarily. It doesn't matter which way you choose. And as before, we are going to assign a spin to each edge. Okay. And here now the spin is the following. So let me write it as CG. So this is the group algebra of G. What this is a Hilbert space with a is a Hilbert space spanned by the group elements of G. Okay, so in general, a state in this space is the superposition of group elements, and we assign such a Hilbert space to each edge. And then, as before, the total Hilbert space is defined to be the tensor product of all the spins over all edges. Okay, and then so according to this assignment, is clear that a basis state in this total Hilbert space is just a assignment of a group element to each edge, right? So we assign we assign a group element to each edge, and that gives us a basis state. For example, I put a group element here, another one here, and I put a group element on every edge. So I will get a basis state. This is the basis state in the total Hilbert space. And as I range over all the possible assignments of group elements, I get a orthonormal basis of the total Hilbert space. Okay, so before introducing the Hamiltonian, let me first define some ancillary operators. So first of all, now for any vertex V and any group element, I define a operator called A sub G of V. So this operator, it only acts on the spins which are adjacent to V. So remember here for the vertex V, it has 4 adjacent spins. And I claim here, I assume I'm going to define this operator so that it only acts non-trivially on these 4 spins. So let's assume that let's choose a basis state on these 4 spins. G1, G2, G3, G4, and also remember that we have chosen an arbitrary orientation on each edge. For instance, something like this. Okay, and then this operator maps this state to the following state. So what it does is to simply multiply G to the spin, to the to the group elements assigned with the spin. So here G1 becomes the GG1. So we multiply G on the left if the orientation on that edge is outgoing from the vertex, like this one, And otherwise, if the orientation is incoming to this vertex, then we multiply the inverse of G on the right. So basically, the orientation determines whether we are going to multiply G on the left or multiply G inverse on the right. So that's the definition of AGV. And you can think of this as a gauge transformation. And it is straightforward to verify the following properties. So AGV times AG prime V, this is AGG prime V. And also at different vertices, all the gauge transformations commute with each other. Okay, and with that, I'm going to define an operator A of V.
There's a V prime there.
Yes, thank you. Yeah, thank you. Yeah, so I'm going to define A of V to be the average of the gauge transformations at vertex V. Okay. And with the above properties, it's straightforward to verify that A of V is a projector. Okay. I'm going to define another operator. Now, for any phase P, I'm going to define operator B of P. And again, it only acts non-trivially on the spins on the boundary of P. So assume, on the boundary of P, we have a basis state as follows. Okay, then it maps this state to the following state. Oh, and also remember there are some orientations on the edge in an arbitrary manner. So, so let me first write it down. So here, this is the delta function. So basically what it means is that we multiply the group elements on the boundary of P. And if the product is the identity element, then BP acts as the identity. Okay? And otherwise, it just accrues that state. Okay? And of course here, because there is orientation involved, so precisely to multiply the elements, we are going to travel along the boundary in the counterclockwise manner, okay? And whenever we travel across an edge, if the orientation on that edge coincides with the direction we are traveling, then we just pick that element. So for example, here we have G1, G2, and now if the orientation on that edge is opposite to the direction, then we will pick the inverse of that element. So here we will pick G3 inverse and then G4. Okay, and we simply multiply them together, and if that is 1, then BP acts as the identity. So that's the definition of the BP operator. And also by the definition, it should be clear that the BP is also a projector, because the eigenvalue of BP is either 0 or 1. So so let's take a closer look at what this means, what BP does. So in terms of a holonomy, so given given a basis state, assignment of a group element to each edge, and given a closed loop gamma, we can define the so-called holonomy along gamma. Basically, the holonomy of gamma is to simply multiply the elements, the group elements on that loop gamma. With that language, BP basically so BP. This operator BP picks out states with trivial holonomy along the boundary of P. Now, in contrast, so we also defined this operator A of V. Remember, A of V is the average of the gauge transformations. So it's not surprising that AV picks out gauge-invariant states. Okay. All right. Another property about these operators, which may not be very straightforward, but is not also not hard to check. So it turns out that all of these projectors, A of V, B of P, so they are pairwise commute with each other. Okay, so basically the only non-trivial part to check is that when the vertex V is on the boundary of the face P, then we need to check that AV and BP also commute, and all other situations are kind of trivial to verify. Okay, so with that, I can define the Hamiltonian H. The Hamiltonian is the negative sum of all the AV operators, and then plus the negative sum of all the BP operators. And you see that this falls into the class of lattice models that I described when defining the topological quantum order. So each operator in this Hamiltonian is a local projector, and they pairwise commute with each other. Okay, and also it turns out that the ground space of this Hamiltonian is frustration free. So the ground space is simultaneously achieved by each term in the Hamiltonian. Okay, so that's basically the definition of the Kitaev model. And here are some facts about it. So here I have defined the model for a arbitrary finite group, and if you like, you can take a simple group as you wish. So in the case of G equals Zima 2, the group with 2 elements, then you will recover exactly the famous Tori code. Okay. And also another fact about Kitaev's model, it turns out the ground state degeneracy depends on the topology of the surface. So it is equal to the following. Now, first of all, consider the group homomorphisms from the fundamental group of the surface to G, okay? And there's a natural action of G on this set by conjugation. Okay, and then it turns out that the ground state degeneracy equals the number of equivalence classes of under this action. Okay, so now I can state the main result. So I mean, I can never memorize these letters, so I wrote it down on my paper. Okay, so so here's the main result. And again, let me first draw a picture. So remember that we have a lattice on the surface, and I'm going to choose some sub-lattices here. Let me call it A, and a larger one. Sorry. Oops. Oh, sorry. Okay, so so let A and B be two sublattices. And we require them to be connected and contractible. Okay, and so here, yeah, A is also a sublattice of B, and B the sublattice of L, and you can see a schematic picture here. And define. I'm going to define a local ground space. So these consist of the states that are stabilized by a subset of the operators. There, I only choose those vertex V in the interior of the lattice B, and only choose the face P, which are a subset of B. So remember, the real ground state is fixed by all the vertex operators and face operators. But here I'm going to define a local ground space. So it's only fixed by the vertex operators contained, the vertex and the face operators which are contained in the sublattice B. Okay. And with that, then for any state psi in this local ground space, normalized, we have so the reduced density matrix of the state psi on the sublattice A. So this is independent of psi. So that's the main result. Basically, what this says is that as long as a state has zero energy within the region B, then its reduced density matrix on A is actually an independent state. It doesn't depend on the choice of the state. Okay, so so this result, I claim that it actually implies both TQO conditions. So to see that, so for example, for TQO1, let's choose a orthonormal basis psi I of the ground space. Remember, the real ground space is the subspace of the local ground space. Okay. And then according to the theorem, we know that the reduced density matrix of psi I is independent of psi I. So let's say, let me call it a rho. And then from here is a simple linear algebra problem to check that this will imply that the reduced density matrix of psi I, psi j must be 0 when I is not equal to j. And then the projector onto the ground space P is given by the sum of psi I, and then from here it can be verified that you take any operator OA, POA P actually is just equal to the trace of rho OA times P. And this is exactly what TQO1 condition. And then to see TQO2, for example, so this reduced density matrix of P, this is equal to the dimension of the ground space times rho, okay? And similarly, the reduced density matrix of PB, again, by the same argument, is equal to the dimension of the local ground space times rho. So now you can see that this two reduced density matrices are actually proportional with each other. Then of course they have the same kernel. So that implies TQO2. So that means that from the main result, it implies the Kitaev's model is indeed a topological quantum order. Okay. Now there are some remarks I want to make here. Now, first of all, the torical case is very easy. You don't have to utilize the main result to obtain this conclusion. It's a simple exercise. And two, in his thesis, Peter Naaijkens, he started Kitaev model on a different setup. So he started Kitaev model on the infinite plane. So it's a different setup from ours. So in our case, the Kitaev model lives on a closed surface. Now in Naaijkens' thesis, he started the Kitaev model on the infinite plane, but it turns out that his method can also be adapted to our case to give an alternative proof of the main result, albeit in the language of one-dimensional algebras. However, we just hope that our proof is more explicit and accessible to the community of quantum information. Another remark is that, so very recently, so in fact, just about a month ago, Yang Qiu and Zhenghan Wang, they had a paper about the Levin-Wen model. So they showed that this Levin-Wen model is a TQO. Again, in the sense that we just described. Now we know that the Kitaev model, in fact, is a subclass of the Levin-Wen model. So essentially, their result actually is more general than ours. However, their difference is their proof of the result is very different from ours. So I just hope that these different proofs can offer different insights to this model. Okay, so now I'm just going to very briefly give a sketch of the proof. If I still have time, when am I supposed to stop?
You have a little under 10 minutes.
Okay. Yeah, so I'm just going to maybe give a very brief sketch. But are there any questions before I proceed? Okay, sketch. Recall that we have a big lattice on the surface, and we have two smaller contractible lattices A and B, something like this. Okay. And also remember that a basis state in the total Hilbert space is a assignment of a group element to each edge. Now I'm going to draw another picture. Okay, so you know, a basis state, a basis is simply I assign, you know, a group element here and here on each edge. Okay. And also given a basis state, here I have a basis state G. This is I already mentioned this, and also given a closed loop gamma. Something like this. A closed loop gamma on the lattice, then we can talk about the notion of a holonomy. So the holonomy of gamma is simply the product of the group elements on the boundary. And of course, we need to take into consideration the orientation. So sometimes we need to choose the inverse of that element, and sometimes we just need to choose that element. But roughly, the holonomy along a loop is simply the product of the group elements on that loop. And let's see what does it mean to for a state to be in the local ground space. Well, first of all, you know, if I have if I consider the BP operator, so BP fix this basis state G. We have seen before this if and only if the holonomy along the boundary of P is trivial. Now we want the state to be fixed by all the BP operators within B. So we want this for any P in B. And of course, this means that you know, the holonomy along any phase contain B to be trivial, and you can actually generalize this a little more. So this is if and only if the holonomy along any curve, any loop in B is trivial. So here gamma, so any loop gamma in B. Okay. And here we actually need to use the fact that B is contractible. Okay. So now we know what the states look like when they are fixed by all the BP operators. Basically, they correspond to states with the trivial holonomy within B. Okay. Okay. So let's see. You know, given let's choose any local ground state. You know, as I said, so this psi can be written in the following form. So it's CG, where GA and G theta. So here I have separate the states into two parts. This is the QDs in A. This is the QDs in A bar, sorry, a complement. And by the above argument, we know that here G must have trivial holonomy in A. Well, we know it must have trivial holonomy in B, but in particular, it will have trivial holonomy on A. Okay. Well, let's also rewrite this state in a different form. So let's collect all the G tutor. Or in other words, let's collect all the states G tutor with the same GA. So something like this. Okay. Where again, G has trivial holonomy. So right now here, this is a unnormalized. Unnormalized state. Okay. So basically now we can put this we can write a general local ground state in such a form, and basically the rest of the argument is to see that actually these states satisfy very special properties. I'm going to make some claims without proof. So the first claim is that so for any G and G prime, again with trivial holonomy in A, such that their restriction on the boundary A is the same. Then there is a gauge transformation U acting on A interior such that so this gauge transformation maps the state G to G prime. Okay. Basically, so basically, whenever two states with trivial holonomy coincides on the boundary, then they are related by a gauge transformation. And with that, this will immediately imply that actually, so phi of G is equal to phi of G prime. So so that means this second part, this state, actually only depends on the restriction of G on the boundary. So let me just write it as phi of G, so restricting on to the boundary. Okay. Okay, so and then now I'm going to so with that we can well, we know that the second part of the state only depends on the boundary of A. So now for H, let's say H is a state on the boundary of A with trivial holonomy. Then I'm gonna consider all the extensions of H to the interior of A. So so G restricts to boundary is H, and again G has trivial holonomy. Okay. And due to the above claim, then we know that the general state psi can be written as follows. So it's H JH A phi H a complement. Okay, so I'm going to finish in just a minute. Yeah, so that's the form of psi. And then the last claim, which will directly imply the main result, is that it turns out that all the states phi H they are pairwise orthogonal and have the same form, have the same norm. Okay. And then once we take this claim, then you will see that the reduced density matrix is proportional to this state. Okay. And this state, you can see that has nothing to do with the initial state psi. And that implies the main result. So the reduced density matrix is independent of the initial choice of psi. And with that, I'm going to stop here. Thank you.
Thank you very much, Shawn. Let's unmute and thank you. I'm sure there are many questions. Are there questions? I'll stop the share.
Oh, sorry, let me see. I think I have a problem with my computer.
No, I stopped your sharing.
Yes, okay.
So are there questions? Well, maybe, Shawn, could you just make a comment about the other part of your title about how it connects more with error correction?
Oh, so actually, this is still a ongoing project. So we know that in the abelian case, so in the case of toric code, or more generally the surface code, it's a stabilizer code, it's a quantum error correcting code, and we know that it has very good properties, such as that its threshold is relatively high compared to a lot of other error correcting codes. So right now we are interested in basically examining the properties of error correcting codes from the non-abelian Kitaev model. And so far, there seems little known along this aspect. And we think, I think at least for certain non-abelian groups, it will have comparable or even better performance at the error correcting code than the toric code. But so far, this part is still a ongoing project. So I can't give you a definite answer for now.
Hello, this is Jun. May I ask a question?
Yeah, sure.
Of course.
In the you mentioned the TQO condition. It seems all the unique ground state of frustration-free Hamiltonian also satisfy TQO condition. Is it right? For example, let's consider cluster state.
You mean if there's a unique ground state?
Yeah, yeah.
If there's a unique ground state, then for sure the first condition, the first TQO condition is satisfied.
Yeah,
but
there's
I
a
think,
second, so let's think about, for example, cluster state.
Yeah.
Yeah, because the correlation function is 0 when the distance is larger than 2. So the reduced density matrix will have the same support. So the kernel, no matter, sorry, I'm not sure.
Yeah, that part I think is not true in general.
Okay.
But the first condition, TQO1, is always satisfied when you have a unique ground state.
Mm-hmm. So I also think for cluster state, maybe the second one is also true.
I don't have a counterexample about that, but I think it may not be true in general.
Okay. But I guess maybe there exists some quantum state which is not topological order state, also satisfy TQO condition.
If you can find such example, I would be very happy, because this TQO condition are supposed to be a definition of a topological order.
What's the intuition? Because my impression about the intuition is the first condition, because it is like error correction code. But
yes.
If we restrict it to unique ground state, then I mean the key point is that people believe it is topological order because the first condition is a topological order. But in the statement of the TQO condition, they do not require this to be degenerate, so it can be applied to system with unique ground state. But in this case, any frustration-free system satisfies this condition. So
yes, usually people just take a TQO1 as the definition of topological quantum order, but it turns out that there are examples which satisfies TQO1 but not TQO2, and those examples you can show that is not stable under local perturbations, so they can't be topological quantum order.
So what's the intuition of the second one? It basically says that if you project out the region outside the region you choose, it is robust to the projection outside the region.
Yes. So basically, what it means is that the local ground state is consistent with the global ground state.
Oh, I see. Okay. Also, no matter what's the boundary condition?
Yeah, so I mean here, you mean the boundary of the subregion or the total lattice? Here I'm just
subregion.
Yeah, that's independent. That's independent on the boundary condition of the subregion.
In this case, it seems cluster state also satisfies this condition, because the correlation length is 0. So if you take any projector outside the subregion, you always get the same reduced density matrix for the subregion for the you will get the same subregion inside the region you choose.
I would be happy to see that. But I mean, that would imply that all the cluster states are topological quantum order.
Yeah. I think, yeah.
You think that's true?
Yeah.
Okay. Well, maybe I'm very happy to discuss more about this with you. Maybe after this talk.
Okay.
Yeah. Maybe you should come, Shawn, to one of our subgroup meetings, and we can discuss it there.
Oh,
Shawn,
okay.
Sure.
Okay.
You why don't you invite Shawn for?
Okay, sure.
Okay.
Are there any other questions from other people? Well, if there are no other questions, then I'd really like to thank you, Shawn, for a very nice talk and a wonderful presentation of your work, and we'll look forward to how it develops. And I also want to remind people of Stefan Holland's talk and David Evans' seminar in 20 minutes. So thank you, Shawn. Thank you.
Yeah, thank you. Thanks, everyone.
Bye-bye. Bye-bye.
Yeah.
Bye-bye.